Cybernetics has its roots in various disciplines and philosophical ideas. The concept of steering or governance can be traced back to ancient Greek philosophy. Plato, in his works The Republic and Gorgias, used the metaphor of steering, Cybernetike, to present the art of government. This idea was later echoed by A.M. Ampere in the 19th century, who introduced the word cybernetic with the same purpose as Plato. The modern field of cybernetics emerged in the United States following World War II. Perhaps most appropriate to deem the origin of cybernetics are the Macy's conferences, held between 1946 and 1953. These conferences, organized by the Josiah Macy Jr. Foundation, focused on circular causal and feedback mechanisms in biological and social systems. Chaired by Warren McCulloch of MIT, the meetings brought together researchers from various disciplines to discuss the principles of control and the role played by feedback. The conferences gained prominence after Norbert Wiener, considered the father of cybernetics, published his seminal book Cybernetics in 1948. Wiener chose the name because the steering of a ship is one of the most ancient examples of a control system, albeit one involving a human link. The first example of an automatic control system is the steam engine governor, originally analyzed by James Clerk Maxwell, who invented the notion of a servo mechanism. Wiener himself made great contributions to the field of control systems as he worked on the fire control problem during World War I. The goal was to design a servo mechanism for a gun that could automatically track and predict the position of a moving target. Despite working for the military, Wiener was heavily against war. His theories were founded upon statistical mechanics and later applied to a vast array of medical problems. Wiener initially defined cybernetics as the science of control and communication in the animal and the machine. Later, British psychiatrist and neurologist W. Ross Ashby promoted it to the science of all possible machines, regardless of their origin. Ashby's work, particularly his 1956 book, An Introduction to Cybernetics, laid the foundation for many of the core concepts and principles underlying the logical and biophysical theories of cybernetics studied in this series. Let's begin with the idea of an operand being acted on by some operation to produce a transform. This whole thing is called a transition, and a set of these transitions defines a transformation. A transformation maps a set of operands into a set of transforms. If all the transforms are contained in the set of operands, the transformation is said to be closed. This one, for example, is not closed, while our original transformation is closed. There are broadly four types of transformations. The 1-1 transformation, where for every operand there is a unique transform. The 1-many transformation, where a particular operand might not have a single unique transform. The many-one transformation, where a particular transform might not have a single unique operand. And the many-many transformation, which is a mix of the previous two. The 1-1 and many-one transformations are said to be single-valued. We can represent a transformation with a so-called transition matrix, where we will denote whether some operand is or is not being changed into some transform with a plus or a minus respectively. Here you can see the corresponding matrix for each of our transformations. We may use a more convenient way to represent transformations. Imagine that our set of operands corresponds to the different possible values of a single variable x. As the transformation acts on this variable, it takes it to a new value x prime, where x prime is equal to some function t of x. We can now use this functional representation to show what happens when we repeatedly apply a transformation to a variable. The value of x at the next time step, for example, can be found by applying our transformation to the result of the previous time step. We may continue this process to obtain the particular sequence of values or trajectory that our transformation generates. A better way to visualize this trajectory is to plot it over the set of operands on which our transformation acts, in order to produce the so-called kinematic graph of the transformation. Here is one for each of the transformations shown as examples. We are now in a position to define what a machine is. It's simply a dynamical system, i.e. a collection of elements which changes its state according to some transformation. We can classify machines according to a few criteria. First is according to the type of transformation it behaves as. Of special importance is the dynamical system which behaves like a closed single-valued transformation, i.e. a determinate machine, for which if you know the current state and the particular transformation, you can predict exactly what the next state will be. The second way to classify machines is according to their complexity. We have defined a system as a collection of elements, but we have actually only considered a simple system consisting of a single element represented by our variable x, where the different possible values of x correspond to the different possible states of our system. But what if our system consisted of many parts? Then the system would become a vector of variables and its state would be specified by the values of the components of this vector at some instant of time. If the system changes with time, we may imagine that it acts as a transformation on tuples of values and that it can be equivalently specified by a set of canonical equations giving the next state of each element as a function of its present state and the present states of other elements. We can imagine each element or part as a machine of its own and other parts which feed into this machine as its parameters. The machine is then called a machine with input or a transducer. We can represent transducers with a diagram of immediate effects, which shows how the different parts of the whole are coupled. For example, the system x1 here is affected by, but it doesn't affect x2. If they both affected each other instead, the system would be said to possess feedback. We can also represent a transducer which is determinate with a matrix, this time giving us the particular transformation that will occur for a variable under each parameter value. For example, if the value of x2 is a, and the initial value of x1 is b, then x1 will be changed to c. Thus, given the initial state of a determinate transducer and a sequence of input states fed into it, one can obtain an exact sequence of output states. Finally, we can also classify machines according to whether they are discrete or continuous. Up to now we have only considered discrete ones, i.e. those that change in steps. If the variables of our system are numerical quantities, then we can easily calculate the amount by which a variable has changed. If we divide that by the duration of our time step, we obtain the rate of our quantity. Now to approach the continuous limit, we want delta to approach 0, so that our difference becomes infinitesimal, and this becomes a derivative. The x now being a continuous function of time. We would want the canonical equations to then give the time derivative of each variable as opposed to its subsequent value. For any system of numerical quantities, we can draw a phase space, that is, a space whose coordinates are the different variables of our system. A point in this space represents a possible state for the system. For any particular transformation, we can consider the set of trajectories it will produce when started from every single point in this space. This set of trajectories is called the field of the transformation. By analyzing the field of a transformation, we can determine the stability of our dynamical system. We have already defined the idea of closure, but now we can state that the idea of stability sits in exact correspondence with that of closure. An unstable dynamical system under some region of phase space is one whose field takes it out of that region. One whose field keeps it inside the region is said to be stable. A special case occurs when the stable region has shrunk to a single point. This point is called a state of equilibrium. It's a state to which applying the transformation results in that same state again. For the discrete case, this means that the change in x is 0. For the continuous case, the derivative of x must be 0. One should note that the whole is in equilibrium whenever all the parts are in equilibrium in the conditions provided by the others. Lastly, we may consider a disturbance or a transformation which acts to simply displace our system from its equilibrium state. Then if t, acting on the displaced x n number of times in the limit that n approaches infinity, results in x again, x is said to be stable under the displacement d. Basically, if the system is eventually brought back to its original state, the equilibrium is stable under the displacement. If it deviates from that, it is unstable, and if it retains the displacement, then we have a case of neutral equilibrium. Let's now put all of this to good use by studying a specific example of a dynamical system, the simple harmonic oscillator. In physics, one could form a phase space from such variables as all the linear and angular positions and momenta for all three axes of all the particles in a system, with their respective forces, torques, and energies. For the simple harmonic oscillator, however, we are considering a mass on a spring which oscillates linearly along the x direction with momentum p. Our phase space is then formed by the two variables x and p. Now the rate of change of the position, or the velocity, is the momentum divided by the mass. The rate of change of the momentum is the force, which for the case of a simple harmonic oscillator is minus kx, where k is the spring constant and x is the displacement of the mass from equilibrium. The negative sign indicates that the larger the displacement, the larger the restoring force in the opposite direction. If we now release the mass with a certain initial position and momentum, the system will trace out an elliptical orbit in phase space. If we consider not just a single trajectory, but the entire field of the transformation, we see that it forms a cycle, and is thus stable along each orbit. One of the more interesting things is what happens when we introduce a damping factor to the oscillation. The system will now spiral down to the center of our coordinate system, eventually reaching a state of equilibrium.